Hello everyone, I'm Mathieu Sorin and I will be presenting the paper A Machine of Few Words, Interactive Speaker Recognition with Reinforcement Learning. This is joint work with Florence Trube, Philippe Preux and Olivier Pietquin. Let's get started. Speaker recognition in the traditional sense is training a machine learning model to identify speakers. So at training time, for example, you have a huge database of speaker alongside a few seconds or a few minutes, more generally, of speech. So you're able to create a voice print for each speaker. And at recognition time, you have what's called a enrollment utterance. It's few seconds, again, or minutes of speech that you need to use to recognize the speaker. So if I give you this voice print, this is a new unseen speech, and you have to guess who is speaking based only on this voice print. So in this case, it's George Clooney. Our setup differs slightly from the speaker recognition settings because we are introducing an interactive part. And this is what makes the paper a bit different from the traditional speaker recognition settings. Because at recognition time, instead of having a fixed enrollment utterance, so instead of having this fixed speech, you're just building slowly and iteratively this enrollment by querying the speaker. So it starts a kind of game where you ask the speaker for a word and it gives you back its waveform, and you have this back and forth until you're confident that you're able to find out who the speaker is. So this what makes the games a bit interesting, because you can have like shorter sequences of nicely selected words, and hopefully you will have also better recognition. So this is what we are aiming for, having shorter enrollment utterances and better recognition. The presentation will be structured like this. I'm just going to introduce again this speaker recognition game to give you a bit more detail about it, because it might be unclear yet how does it works. I'll be also introducing reinforcement learning and how you can model the querying mechanism and how you can also optimize this process, giving you also a brief overview of the dataset and how we process the raw speech, and finally give you some experimental results to back up our claims that we did at the beginning. This is an overview of the speaker recognition game. So as a traditional speaker recognition task, you have, of course, to identify a speaker. But instead of trying to identify the speaker among all the people present in the database, we're going to restrict the choice among what we'll call a list of guests. So at each episode, we sample a subset of the whole database that we'll call the guest list. And among these guests, we pick a random speaker. Of course, the model doesn't have any clue who the random speaker was how he was selected. But what he can do is just he can query the speaker by asking him to pronounce some words. So for example, he asks cat, the unknown speaker pronounce the word, etc. You have this back and forth until the speaker recognition module is able to identify the speaker. Of course, this process is repeated many times. You have many episodes, so you have multiple guest lists that are sampled, multiple speakers, and hopefully at the end, he's able to identify the speakers, to adapt its strategy to the speaker that he is querying, and to generalize also to new speakers that we will see at the end. To simplify the architecture and the model used, we are going to split the speaker recognition module in two parts. So because it has, in fact, two jobs in a sense. The first one is once you queried all the word and you have all the voice prints, you're able to find the speaker. So this is what we will call with the guesser model, because he's guessing based on the history of word that was queried. So this can be trained using like traditional classification, and overall this model really looks like a traditional speaker recognition module. And the real innovation here is the enquirer model, which query words iteratively to identify the speakers. And this is the real contribution of the paper. And this is what is trained using reinforcement learning that I will be describing a bit later. before diving into the meat and potato of the model, I'll just start briefly by recapping what the guesser model is. It's really a traditional speaker recognition model. It takes as input the word history, so it would be the enrollment in traditional speaker recognition, and this is the voice prints of all the guests that you are currently facing, and you have to choose among this list of guests who is speaking. So in this case, it's Bob. And the actual model the actual guesser model is a neural network that is trained using cross entropy loss. This can be a bit surprising for you speaker recognition expert, because most of the time you use PLDA or other technique. I mean, nothing prevents you from using PLDA in this setup. Just we wanted to start simply by having a really simple model, but yes, we in the future we will be using PLDA or other advanced technique to train this guesser model. This is going to be a very quick introduction to reinforcement learning. So in reinforcement learning, you have an agent that is interacting with the environment, is acting based on what's called a context or state. It will most of the time be a state in the reinforcement learning literature. And the agent is optimizing what's called a reward function. So I'm just going to give you an example, a concrete example. It would be easier to understand the setup. So in our case, for example, what the action are choosing a word. So at each time step, your agent will be selecting a word, and he can choose his action based on all the guest lists, so all the guest embedding, and the history of words that were already queried. And what he's optimizing is a reward that will get only at the end after multiple interaction. You will get 1 if the guesser is right, he got the good speaker, and 0 if the guesser is wrong, he misclassified at the end the speaker. So the goal is really to optimize this enquirer, and the only signal that it gets is at the end whether the guesser is right or wrong. So we cannot use traditional classification, and we have to use reinforcement learning because he has to plan in advance and he has to react based on which waveform he got back from the speaker. To ground a bit more this reinforcement learning setup, I'll just give an overview of the enquirer model, just to give you a bit of insight of how it works. So again, at each time step, the enquirer has to select a word. This is its action. And he must choose this action according to 2 information, the list of guests available and the list of word that he already queried. So he already asked for the word cat and for the word drunk, and he has to adapt its policy. He has to adapt its word choice based on the signal that he received. And this is very important because in advance, since you don't know what is the result of your action, because if he asks for the word house, he doesn't know in advance which waveform it will get because he doesn't know who is interacting with. So this is important to really take into account the signal that you already received to adapt your policy and to adapt your word choice in the future. So you don't have access, of course, to the waveform beforehand. And in our setup, we simplified again a bit. We have a fixed number of words to choose from. So he has a list of 20 words that he can choose from and to query the speaker. And he has a fixed number of query, which means that he cannot query unlimited number of words. We fixed this to simplify again the guesser model. Now that you have all this model, you can again pick your favorite reinforcement learning algorithm to optimize the action selection and to optimize the reward at the end, because this is really what you are looking for. I don't give you more details about the reinforcement learning. You can look about that in the paper. Again, the algorithm choices, because for example, we choose PPO, but there is many other reinforcement learning algorithm, but we give more detail about this in the paper. The dataset we used in this paper, it's called TIMIT. It's a pretty well-known dataset in the speaker recognition community. It is composed of 630 speakers, mostly of American English. And what's important is that for every speaker, you have 8 specific sentences that are specific to the speaker. So every sentence is different and they're used to build the voice print of each speaker. And what's also important is that 2 sentences were pronounced by every speakers. So we know that for certain words, every speaker will pronounce them. So it enables us then to query those words, and we know that the speaker will be able to give this this information because he pronounced the word. We know that since they're common sentences. The pre-process steps was pretty common speaker recognition pre-processing. We downsample the raw waveform, we extract the MFCC, and then we use what's called X-vector extraction. So it allows to extract a fixed vector length for every utterances. So what it enables is that you have a pre-trained network that already encode higher level information about each speaker. And we use this X-vector extraction on both the voice print and also for every word. So we already have some kind of high level information regarding the waveform of the speaker. Now that we have all the necessary ingredients, I just wanted to highlight what are the questions that we want to answer with our experiments. So the first one is, can the enquirer learn a policy, a word choice that is able to help the guesser? And this is the core of the paper, is whether it's able to increase the recognition score compared to just random sampling among the words. So this is the first question. The second question, is, which is also important, is that whether the policy adapts to the speaker that is being inquired. And this is quite important too, because we don't want our word choice to be fixed for every speaker. We want the policy to adapt to the speaker that is querying, because if not, it means that it just selects always the same word, and it's not a very interesting policy. And the last question, which is a bit more subtle, is that whether the policy is able to take into account the context. It means that if the guest list is very different from one another, is able to adapt. For example, if we have many speakers from Texas, the word choice that we'll be using will be quite different if every speaker is from a different region of America. So adapting word choice to also the context is also important. To compare our algorithm, we use 2 baseline. The first one is just a random sampling among all the possible words. So this is like, in fact, traditional speaker recognition model use this technique because the enrollment utterances is just random sampling of words. And the second baseline, which is a stronger one, use a random sampling, but among a hand-selected list of discriminative word, which means that instead of using the 20 word that you can pick from, we just hand-picked words that are longer and more discriminative than just, for example, h or the, which are not very interesting. After a few steps of optimization, our enquirer is able to design a policy that really helps the guesser. It really increases the recognition score beyond the random baseline, which is just selects words randomly, and the handcrafted policy that just selects among a curated list of good words. So that's good news. We have a policy that's able to increase the recognition score. And we also looked at the word diversity by computing the Jacquard index. If you want to look, there are some details in the paper, but just to guide a bit, a deterministic policy gets a score of 1 when it outputs always the same word. A random policy gets a very diverse score because the word output are really random. And the trained inquirer is located between those two, which means that he's able to have a policy that adapts to the speaker, but not falls to the deterministic regime. So that's good news. We're able to learn a policy that adapts to the speaker that is being inquired. So I guess the conclusion is turn your classification task into interactive one, and you might increase the scores. That's what we showed. We're able to, instead of using a fixed enrollment, we're able to build it iteratively, and it increased the overall recognition capability. So thank you for listening. And if you want more details, you can ask a question or look at the paper. Thank you.